Some of the most exciting math we get to do in first year calculus is solving what are called separable differential equations. We've already been solving differential equations. We've been solving differential equations, remember that's just any equation that contains a derivative, by thinking in our head, or now we can use integration by substitution, finding an antiderivative of the derivative to find a solution to the differential equation. And it might be a general solution if we don't have an initial value problem, or it might be a particular solution if we have an initial value and we can figure out what that plus c value really is. So just notice that all of the derivatives we've undone, all of the derivatives in our differential equations have been derivatives that are functions of x only. But remember from our work with implicit differentiation that a derivative is sometimes a function of both x and y. And we saw that with some of the slope field diagrams we were making. We were making slope field diagrams for derivatives that had both x and y in them, and we saw how that changed our picture. So this is sort of that next step up. This is the mathiest that first year calculus gets. We're going to solve differential equations where the derivatives are functions of both x and y. Now let me warn you before we start that, again, you're going to take a class in college called differential equations, and you will solve like 20 times more differential equations than we're going to solve. The kind of differential equations we're going to solve form only a very teeny tiny percentage of all the differential equations in the world. For us to be able to use techniques of first year calculus to solve them, they have to be what we call separable. That means we can move all the x stuff to one side and all the y stuff to the other. So when I say separable, that means being able to separate the x and the y to two different sides of your equation. If you try to solve a differential equation by separating the x and the y, and you find that they are not separable, then you're not working on the right thing. You won't be able to solve a differential equation that is not separable. So let's try our very first one. If I want to solve this differential equation, dy dx is x squared y squared, and I've been given an initial condition. So I'm going to, you probably guessed, try to find antiderivatives. An antiderivative that, if I took its derivative, I would get x squared y squared. Well, that's going to be, my setup is going to look like this. So here's how I'm going to start. I want to have everything that has a y on the left-hand side. I want to move everything that has an x in it to the right-hand side. So we've talked about how dy dx is not really a fraction, but you could think about multiplying both sides of this equation by dx. So my new equation, dy equals x squared y squared dx, is a little bit closer to separated. I at least have all the x's are on the right, but I have this problem where I still have some y's on the right too. So you just have to think about what undoing operations you would use to get the y squared back over to the left-hand side. Well, y squared is multiplying on the right-hand side, so I'm going to divide both sides of this equation by y squared. And this is what I get as my answer. I'm going to have dy over y squared equals x squared times dx. Now I would say my differential equation is separated. I have the y's on one side and the x's on one side. If you got this far on the AP test, that's worth 1 point, simply for separating the variables correctly. So what do I think I'm going to do? I'm trying to undo derivativing. Oops. Undoing derivating means finding an antiderivative. And now that I've done section 6.2, I know that a notation I can use that means find an antiderivative is the indefinite integral. So this is the notation we use. I would say I'm going to integrate both sides. So, I mean, what does that look like? It looks like I'm going to slap an integral sign on both sides. So if dy over y squared equals x squared dx, then the integral of dy over y squared equals the integral of x squared dx. There's no special reason why that 2 is floating up so high in the air. That's just the same x squared as it was in the line before. Now I'm going to have to integrate both sides. That means I'm finding an antiderivative. So I'm hoping that when you look at the right-hand side of that equation, you think it's not too bad. How can I find an antiderivative for x squared? The antiderivative for x squared is add 1 to the exponent, divide by the new exponent, and that's going to be x cubed over 3. On the right-hand side, you had a problem similar to this on your last practice test. Probably the easiest way to do that on the left-hand side is to think of that as y to the negative 2. So how would I find an antiderivative for y to the negative 2? I would add 1 to the exponent, so new exponent is negative 1. Yeah, so if I want to integrate dy over y squared, that's the same as the integral of y to the negative 2 dy. So I'm going to add 1 to the exponent, that's going to be y to the negative 1, divide by the new exponent. Okay, so two things. Don't forget, I'm going to have to add a plus, I'm going to call it, well, I'll call it c. Notice you could rewrite this expression, y to the negative 1 is the same as 1 over y. And that negative 1 makes the result negative. All right, so watch what I've done here. Okay, so I didn't simplify that over there. So negative y to the negative 1. Just notice that I integrated on both sides, and so I'm going to need a plus c, right, for each of those antiderivatives that I found. Well, here's the thing. This is fine, and feel free to write that. But notice that I could subtract c1 from both sides. And then on the right-hand side, I'd have x cubed over 3 plus c2 minus c1. But c2 and c1 are just some constant, so we sort of make a decision. We have a convention. As calculus fans, we just combine both constants and we put it on the right-hand side, the side with the x's. So imagine that I subtracted c1 from both sides, and now instead of c2 minus c1, which is just some constant minus some constant, I just gave it a new name, which is capital C. So you won't ever have to trip up over that. That's sort of like the next. You'll just get used to that. But that's what happened. If you want to know why there's a C on one side and not on the other, it's that there was a C on both sides. We've just combined the constant, we call it the constant of integration, onto one side. We'll talk lots more about scoring on the AP test as we start practicing. There are exactly 108 points possible on the AP test. If you can get about 70 of them, you'll get a 5. So just to put that in perspective, each one of the there are 6 free response questions. Each one is worth 9 points. And typically, solving a separable differential equation is worth typically 5 and sometimes 6. So I already told you that you would have received 1 point at this place for having successfully separated the variables. Here I would expect you received 1 point for getting both antiderivatives correct and another point for remembering your plus c. If the antiderivatives have been a little more complicated, you might have received 2 points for the 2 antiderivatives. So we have 2 things left to do in this problem. We are supposed to report the function y, which means we're going to have to isolate y. And we've been given an initial value. Was it 1, 1? I'll have to look it up in a second. And we need to make sure that we use that initial value so that we don't have a c in our answer anymore. And to be frank, at this point you could proceed in either direction. You could start by finding c, or you could start by trying to isolate y and find c later. But you're going to have to do them both, so feel free to do the one that makes sense to you. If you wanted me to guess where the errors are least likely to occur, it would be by substituting in your initial condition to find c. And if you did that, you would get the point for finding c, and then even if you made a mistake while you're finding y, you've got your 4 points out of 5 in the bank. If you make a mistake while isolating y, even if you later find c correctly, you might not get the point. So I'm going to do that Just notice you could proceed by isolating y first if you prefer. I'm going to start with my initial condition and try to solve for c. Okay, so I just checked, and in fact my initial condition was 1, 1. So I'm going to take this equation that I have at the bottom, negative 1 over y, but I'm going to replace the y with 1, equals, I'm going to replace this x with 1, cubed over 3, plus c. So I'm going to write negative 1 equals 1 over 3 plus c. I'm going to try to isolate c. And that tells me negative 1, take away 1/3, so negative 4/3 equals c. So here's what I do. I'm going to start with the equation I had down here, but now I know that c equals negative 4/3. So I'm going to jump all the way up to the top with this equation starting over, but I'm going to replace my c with negative 4/3. So I've got negative 1 over y equals x cubed over 3 minus 4 over 3. I have two things to do. I'm trying to isolate y. I notice y is in a denominator accidentally instead of being in the numerator where I want it. And I notice I have a negative over there multiplying my y when really I don't want one. So you could actually, you've got some choices, but I'm going to multiply everything through by negative 1 so that I get y, 1 over y equals. I notice in my next step, I'm going to want to flip the left-hand side over. So in preparation, I'm going to write the right-hand side of my equation as one single fraction. So instead of x cubed over 3 minus 4 over 3, you could write negative x cubed plus 4, because remember I'm multiplying through. That's the same as 4 minus x cubed for people who don't like to lead with a negative sign. And that's good. Now I have one fraction on the right, one fraction on the left. My last step is to flip both. Let's be very clear. I can flip both sides of this equation so I get my y where I want it. That only works because I had one single fraction on the right-hand side. Don't try to do that if you don't have one single fraction. If you prefer, you could cross multiply. There are lots of options. That's 3 over 4 minus x cubed. I think this is my solution, but I hate to leave anything to chance. So I'm going to at least do this thing, which is I was supposed to report a solution for which when x is 1, y is 1. So I'm absolutely going to try to guarantee my point on the AP test by replacing the x and y both with 1 and making sure I make a true statement. 4 minus 1 cubed. Does 1 equal 3 over 3? Yes. If you want to, you could take that next step. If it's the AP test and you have like 10 minutes left at the end and nothing else to do, go ahead and check your solution to your differential equation by doing whatever math it takes to make that derivative look like, to take the derivative of this y function that you found and make it look like the original derivative, which I think was x squared times y squared. Okay, remember there was one other thing we had to do when we were reporting our solutions to differential equations, and that was to notice if there was a discontinuity in our solution, we had to say which branch of this y equals 3 over 4 minus x cubed function was the solution to our problem. So this function, y equals 3 over 4 minus x cubed, has a discontinuity at the place where 4 minus x cubed equals 0, because that's what makes the denominator equal to 0. That's the same as saying 4 equals x cubed, so saying that x is the cube root of 4. So now I have to ask myself, the one ordered pair that I knew, which was 1, 1, I look at that x value. So there's only one x value that gives me a problem. That's the place where x equals the cube root of 4. So the function y, my solution function, is continuous from negative infinity to cube root of 4, and again from cube root of 4 to infinity, but not including that exact place, cube root of 4. So I have to ask myself, is the place where x equals 1 to the left of or to the right of cube root of 4? Well, cube root of 4 can't be 1, and it can't be something smaller than 1, because if you took 1 and cubed it, you would just get 1. So you need to cube something bigger to get 4. So it tells me that 1 is to the left of cube root of 4, and I would say that this solution is good on the domain negative infinity is less than x, which is less than the cube root of 4. So this is my solution, y equals 3 over 4 minus x cubed, and my solution is good on the domain negative infinity is less than x, which is less than cube root of 4.